Let's continue our discussion on Laplace transform properties. And the first things we will look at here are the properties that are with respect to the region of convergence. So we have already looked at these in detail and we have proved some of the initial properties. So just to recap the statements, property 1 says, in general, the region of convergence consists of vertical strips on the S-plane. A region of convergence depends only on the real part of S, sigma. Property 2 says the region of convergence should not contain any poles. Obviously, poles are the points in the S-plane where the functions go to infinity. That's not where it is finite, so it should be excluded from the region of convergence. We looked at the definition of right-handed and left-handed signals, a finite duration signal, and a two-sided signal. We also looked at how these signals, right-handed, left-handed, finite duration, and two-sided signals, how are their region of convergences in the S-plane. So for example, for a right-handed signal, we saw that the region of convergence should be to the right of the rightmost pole. Similarly, for the left-sided signal, the region of convergence should be to the left of the leftmost pole. For a finite duration signal, it should be all of S-plane. This is coming up in property 3. And for a two-sided signal, it should be a vertical strip. We have also seen that in an example earlier. Property 3 says a signal which is square or absolutely integrable and has finite duration has a region of convergence of the entire S-plane. We proved this as well. Coming to property 4. Property 4 says if x of t, the time domain signal, is right-sided and there is a line, vertical line, sigma equals sigma sub 0 in the region of convergence, then any other line, vertical line, sigma 1 with sigma 1 greater than sigma sub 0 is also in the region of convergence. In other words, we can say that for a right-sided signal, the region of convergence it should be to the right of the rightmost pole, and it goes on towards the positive direction. We proved this property as well. We looked at what happens when the signal is left-sided. If it's a left-sided signal, then our region of convergence will be to the left of the leftmost pole. The example we looked at only had one pole at origin, so the region of convergence was to the left of that. Now coming to property 5, which is something that's new. We have not talked about this yet. It is related to property 4. This is very similar to an earlier property, property 4. So we are not proving it here because we have already proved property 4, but it is with respect to the left-sided signal. So if x of t is left-sided and there is a vertical line sigma equals sigma sub 0 in the region of convergence, then any other line, vertical line, sigma equals sigma 1 with sigma sub 1 less than sigma sub 0 will also be in the region of convergence. In other words, region of convergence for a left-sided signal will be to the left of the leftmost pole. And the proof is similar to property 4. We don't need to do that again. Now a quick clarification about the Laplace transform of e to the negative absolute of t. This is example we looked at in the previous class. There's a clarification that needs to be made here. So e to the negative absolute of t is a two-sided signal. We have seen this earlier. So its region of convergence should be a vertical strip, as it is shown over here. It is a vertical strip excluding the poles at 1 and minus 1. It is a vertical strip there in the S-plane. Real axis is sigma, imaginary axis j omega. Now the clarification here is that the Laplace transform of e to the t for negative time is actually 1 over 1 minus s. I earlier had it as 1 over s minus 1, and thankfully a student caught me there, and this is the correct version, 1 divided by 1 minus s. So the pole locations don't change, the region of convergence doesn't change, just that factor changes, which means the Laplace transform the function in S domain changes slightly. Now, in the earlier example, we saw how we mark the poles at plus and minus 1, and then we find the intersection of the regions of convergences of these two pieces. One we highlighted in yellow and the other we highlighted in blue. We individually looked at its Laplace transform. We find the intersection of the regions of convergences to see that it is going to be a vertical strip. Property 6 says if x of t is two-sided, just the example that we saw, then if it exists, the region of convergence consists of a vertical strip in the S-plane. Now, two-sided essentially means the support is unbounded on left as well as on right. And for this particular signal x of t, if the Laplace transform exists, then it is going to be a vertical strip in the S-plane. Now, the question is there going to be any such situation where you have a two-sided signal and the Laplace transform doesn't exist? Absolutely, that is possible. Because if the signal is not absolutely absolute integrable, we look for f of t e to the negative st. That has to be absolutely integrable. If it is not, then the Laplace transform does not exist. We looked at the existence of Laplace transform condition earlier. Now, property 6, we can validate that quickly by looking at the previous example where x of t was e to the minus absolute of t, and it was a two-sided signal, and the region of convergence happened to be a vertical strip. Now, we can also view this as this is going to be a left-sided signal, the yellow piece, so its region of convergence will move left. This guy in blue is a right-sided signal, its region of convergence will move right, and there is going to be an intersection which will have to be a strip, vertical strip. All right, moving on to property number 7. If x of s, the function in Laplace domain, is rational, then the region of convergence is going to be bounded either by poles, or if it is unbounded, it's going to extend to infinity. So for example, when we had an impulse in the time domain, its region of convergence actually extended to all of S-plane, so extends to infinity. But it could also be bounded by the poles. Note, poles should not be in the region of convergence. Now, property 8 kind of summarizes the things we have been talking about earlier. If x of s is rational, then x of t is right-sided. There could be two things. If x of t is right-sided, then the region of convergence is to the right of the rightmost pole. And if x of t is left-sided, the region of convergence is going to be to the left of the leftmost pole. So if we know the classification of the time domain signal, right-sided versus left-sided, then we can pick out the region of convergence for those signals. Now let's take a look at this in with an example. So if here we have the function in S domain, cap x of s. It's a rational function 1 divided by s plus 1 times s plus 2, and we are asked to sketch the possible regions of convergences. Clearly, this function has two poles. One is at -1 and one is at -2. So I have quickly marked the pole at -1 here, here, and here, 3 such cases, because I know that the possible regions of convergence could be in 3 cases. So that's in yellow. The second term here in the denominator, which is s plus 2, which gives you a pole at -2, those are going to be marked by blue lines over here. So what are the possibilities of region of convergences? They should exclude the poles and they can extend towards infinity. So if I start off all the way to the left, one possibility could be if I can sketch 2 straight lines, say in gray, right there, and another one right here, then actually I'm going to copy this and paste it here and here as well, so that I can repeat the shading of possible regions of convergences again. All right, so 3 possible regions, right? One is going to be to the left of the leftmost pole, one is going to be a vertical strip, the other one is going to be the right of the rightmost pole. So let's start all the way to the left here, and let's use green to indicate region of convergence. So I'm going to quickly shade, excluding that vertical line, everything to the left of that leftmost pole. So that is going to be the region of one possible region of convergence. And for the second case, it's going to be a vertical strip. So that would mean that the signal in time domain is a two-sided signal. Now notice I'm trying very hard to exclude the poles here. So vertical strip there, and the last one is going to be everything to the right of the rightmost pole, extending towards infinity. So for these three regions, when are they going to be which one? So for example, all the way to the left, we have region of convergence as real part of S less than -2, which means that the signal is left-sided. Now the next one, it is a vertical strip. So the region of convergence actually is between -2 and -1. So -2 less than real part of S less than -1, and the signal classification here is going to be two-sided signal. And the last one over here is obviously going to be a right-sided signal. Region of convergence is real part of S greater than -1, and it is going to be a right-sided signal. So by looking at the region of convergence, we can talk about where that classification of that signal. So right versus left versus finite duration versus two-sided. All right, let's take a look at another example over here. We have an inverse Laplace transform to find. We are given x of s. So the given x of s is exactly the same as before, 1 divided by s plus 1 times s plus 2. And the region of convergence, there were three possibilities. Over here, we have picked one. The one we have picked is real part of s greater than -1. So it is the one to the right here, the rightmost one. So we know that the signal is going to be right-sided. We can actually use that in order to find the inverse Laplace. Let's take a look. X of s, let's first use partial fraction expansion to write x of s as 1 divided by s plus 2 minus 1 divided by s plus 1. A little bit more about partial fractions in a few minutes. Now once we use partial fractions and divide this up, now we have divided this up into two fractions, and we know the inverse Laplace of each of those fractions. So that's the reason why we are using partial fractions. We are given that the region of convergence is greater than -1. That's the statement. That was the problem. So this means that this is only possible when both the region of convergences are to the right of their poles, which means if I look back at this example here, because the region of convergence is found by finding the intersection of the individual regions of convergences, we have two poles, one at -1, one at -2. They are both coming from these two fractions here. One is with yellow and the other one is with blue. I've used yellow for -1. I think I use, yes. So the only way I can get this as the region of convergence is if both the poles had their region of convergence going to the right. That's the only way I can get that intersection. So we know that both of these are individually going to be right-sided. Now to find the signal in time domain, we find the inverse Laplace of 1 divided by s plus 2 minus carries over inverse Laplace of 1 divided by s plus 1. So 1 divided by s plus 2 is going to be e to the -2t u of t from an earlier result. But for this, the region of convergence is going to be a real part of s greater than -2. Now you see what we did. We chose a right-sided signal here because we know from earlier that both of them have to be right-sided in order for this to work out. So e to the negative t u of t minus e to the negative t u of t as well. So for both of them, the region of convergence is to the right of -1 here, to the right of -2 here, so that the intersection comes out to be the problem statement. And then we can rewrite this result in a nice form: e to the negative t minus e to the negative t. You take the common factor u of t out. So that's how we would use the region of convergence along with x of s to find the inverse Laplace. Now clearly, if it was a vertical strip, then one signal would be right-sided, one signal would be left-sided. If the region of convergence over here was left-sided, the first case here, then both of these would have to be left-sided. Moving on. Now, how do you find the inverse Laplace of rational functions? So now the discussion is going to be related to partial fractions and very, very generic view of how do you deal with a polynomial in the numerator and a polynomial in the denominator. So assume that the Laplace transform cap f of s in the Laplace domain can be written as a ratio of polynomials in the complex variable s. Now we are writing f of s as some polynomial in the numerator, cap p of s, and some polynomial in the denominator as cap q of s. We are doing all of these partial fractions in order to get them into this form, 1 divided by s plus a, so that we can use the standard Laplace transform pairs to write the function in the time domain. Cap p of s is the numerator polynomial. The roots of p of s are called as zeros of the function f of s. The denominator, q of s, that's the denominator polynomial, the roots of which are called the poles. So the poles are points where f of s goes to infinity. Zeros are points in the s-plane where f of s goes to 0. Now, how do you find inverse Laplace of f of s? We would first need to decompose f of s into smaller fractions using partial fraction expansion, and then find inverse Laplace of each of them, of each term. So let's look at that partial fraction decomposition. F of s represented as the ratio of two polynomials. The polynomial order could be different. So for example, in the numerator, we have an order m. The highest power of s in the numerator is m, hence the order of that polynomial. And in the denominator, we have another polynomial in s whose order is n. So the highest power of s in the denominator is small n, and hence its order. We have arbitrarily chosen some coefficients for s, s squared, s cubed, and so on for both the numerator as well as the denominator. Now, f of s, what about proper and improper fractions? F of s, the rational Laplace transform, is proper if the order of the numerator polynomial is less than the order of the denominator polynomial. And it is going to be considered as an improper fraction if f of s has the order of the numerator polynomial greater than or equal to the order of the denominator polynomial. Now we know that we can convert an improper f of s into some function of s plus some proper function, proper fraction. And we can do that, but we would need to use polynomial division to find this polynomial function first, which I'm not going to deal with over here. I'm going to focus on the proper function part, and then how do you write the partial fractions for that proper function. So let us assume that q of s is fully factored. We have the following cases that we will consider for partial fractions of proper functions. I'm only considering proper functions here. We are not going to talk about polynomial division. If there is a need for you to do a polynomial division, I assume you all will be able to take care of that. So partial fractions for proper f of s. How do I do it? Case 1. Q of s, the polynomial in the denominator, has distinct linear factors. So that means that the roots of the denominator are distinct, no overlap, no common roots, no repeated roots. I have everything that is distinct. So that, which essentially means that Q of s should be able to be factored as s minus lambda sub 1, s minus lambda 2, and so on up to s minus lambda n. In this case, I have n roots, which means that I have n distinct roots of Q of s, n poles for f of s. Then I can write f of s as k1 divided by s minus lambda 1 plus k2 divided by s minus lambda 2, and so on up to the last term here, k sub n divided by s minus lambda sub n. Now all that is left over is to find k1, k2, so on up to kn, and once I do that, I've found all the partial fractions for f of s. Now based on the region of convergence that is specified, we would determine the signal in the time domain. So individually we would take a look at each term, and depending on the region of convergence we would find the inverse Laplace. An example we have seen earlier. Now k sub I, any numerator constant over here, can be found using this identity. K sub I equals s minus lambda sub I, that particular distinct root, multiplied by f of s, which is p of s divided by q of s, evaluated at s equals lambda sub I. Now let's take a look at this example here. We have 3s divided by s minus 1 times s minus 2. So it's a proper fraction because the order of the numerator polynomial is 1, the order of the denominator polynomial is 2. So it's already in a prop. So let me write that down actually. So m is 1, n is 2, which means it is a proper fraction. So we don't need to do any polynomial division here. Now that means that I can use case 1 provided I have distinct linear factors. I can quickly glance Q of s. Q of s has two roots. One is at 1, the second one is at 2. That means they are distinct. So I can use case 1 for this example. So I should be able to write this function as k1 divided by s minus 1, and I will have k2 plus k2 divided by s minus 2. So if I find k1 and k2, I should be done. Now I can find k1 by evaluating. If I multiply s minus 1 with this, what do I have? I essentially will have this part that remains, and I would plug in s equals lambda sub I. So plug in 1 there, right? So if I plug in 1 there, I'm going to get 3 times 1 divided by negative 1. So that's negative 3. So I know that instead of writing, so here, actually I can continue here as negative 3 divided by s minus 1. That would be my first partial fraction. I'm going to erase this quickly and then look at the second one for k2. So for k2, I'm going to essentially multiply this by s minus 2. So that cancels out. And I'm going to evaluate that function highlighted in green at 2. So I get 3 times 2, that is 6 divided by 2 minus 1, 1. So I get 6 here. Plus 6 divided by s minus 2. Now once we do this partial fraction, this is ready for you to take the inverse Laplace transform. We would also need the information about the region of convergence in order to complete the inverse Laplace. Without that, we cannot find x of t, or the function in the time domain. Okay, so still need ROC to find a function in the time domain. All right, let's move on here to case 2. Case 2, the denominator polynomial Q of s has complex conjugate roots. So let's try to see that only 2 roots. One is at r and the other one is at r complex conjugate. So f of s is written as p of s divided by q of s. In the numerator, you have a polynomial of order 1, as plus b. In the denominator, we have a polynomial of order 2, s minus r multiplied by s minus r complex conjugate. In that case, I can write f of s using partial fractions as two terms. One of them is some constant c divided by s minus r plus that same constant conjugated divided by s minus r conjugate. And you evaluate c by simply multiplying the function f of s by s minus r and evaluating that function at s equals r. Something similar to what we have done before. So that's how we would handle complex conjugate roots with case 2. All of this, again, being done so that we can break up f of s and write terms to be able to use the standard Laplace transform pairs. Next is q of s has repeated roots. So here there are many roots. Let's try to take a look at which ones are repeated and which ones are unique. They're distinct, because both of them are present here. So f of s is written as p of s divided by cap q of s. You have polynomial in the numerator as is p of s. I'm just going to assume that p of s, the order is less than the order of the denominator. Actually, the order of the denominator is r plus n. There are repeated roots here. So let's just quickly highlight the r repeated roots. That's r poles that are on top of each other at the same location. So those are r repeated roots. And there are also n distinct roots here. There are n unrepeated roots. So for all of that. All right, so q of s clearly has n unrepeated roots, and the root alpha, only one value that makes the denominator 0 for the repeated part, repeats r times. In that case, f of s can be broken up into many terms. First, you have all the distinct or the unrepeated roots here. So let me highlight the using yellow, because we have been using yellow there. That is for the unrepeated roots, n unrepeated roots. And how do you evaluate k1, k2, k3, k4 and so on up to kn? We are going to use simply the same step that we used for case 1. K sub I evaluated by multiplying the rational Laplace transform by s minus lambda sub I and evaluating f of s at s equals lambda sub I. Now coming to the repeated roots here. For repeated roots, I'm going to have to find some coefficients a sub 0, a sub 1, a sub 2 and so on. Actually, these are all repeated roots. And the difference in this is going to be the decreasing power in the denominator for s minus alpha. So r minus 1 and so on up to all the way down to 1. So if we are able to find k1, k2, k3 and a sub a1, a2, a0, a1, a2 and so on up to a sub r minus 1, we would have broken them into all the terms, partial fractions, and then we can do the inverse Laplace from there. So k sub I, we have already dealt with that. Now a sub I can be found by using these results. So a sub 0 can be found by multiplying f of s by s minus alpha raised to r and evaluating that at alpha. A1, same thing, but differentiate it with respect to s once. A2, differentiate it twice and multiply it with half, and so on. So any arbitrary coefficient a sub m can be evaluated by finding 1 over m factorial, the mth derivative with respect to s of s minus alpha raised to r f of s evaluated at s equals alpha. So find s minus alpha raised to r f of s and its derivative r times, and then plug it into these a0, a1, a2 and so on up to am calculations. Once you have those coefficients for a's and k's, you put them into each terms, then find the inverse Laplace given the ROC information as well. All right, so these are very generic results. Obviously the problems are not going to have a lot of these terms, but you are going to need these for repeated and unrepeated roots. All right, let's talk about how do you find the inverse transform with repeated roots for Q of S. So here we are going to try to use the differentiation property, so which is differentiation in the S domain is going to be equivalent to multiplying in the time domain by t. That's the property of derivatives that we have looked earlier. So when you differentiate in the S domain, you multiply by t in the time domain. So if you have a real part of S greater than lambda, that's the given that, then the Laplace transform of e to the lambda t u of t is going to equal 1 over s minus lambda. We have seen this with, I believe, e to the at u of t. And we have found the region of convergence for that as well. Now, what would happen to this when we multiply in the time domain by t? When you multiply e to the lambda t u of t by a factor t that's in the time domain, we know from the differentiation property that I'm going to have to differentiate. Let me use this connector here. I'm going to have to differentiate in the S domain with respect to S and a minus sign as well. So here I'm going to be doing that differentiation for 1 over s minus lambda. So if I do the differentiation and I incorporate that negative sign, I'm going to get 1 over s minus lambda squared. So that means that the inverse Laplace of 1 over s minus lambda squared is t times e to the lambda t u of t, where the real part of s is greater than lambda. That would define your ROC. Now zoom out and try to take a look at what happened. Your power in the exponent went up by 1 while your time domain signal got multiplied by t. So we can use this result to establish a pattern. The inverse Laplace of 1 over s minus lambda is e to the lambda t u of t. So for all of these, the region of convergence is the same. Real part of s greater than lambda. We already did the first step here. Inverse Laplace of 1 over s minus lambda squared is t e to the lambda t u of t. So you multiplied with t here because you had a 2 there. And when you do this another time, you get t squared divided by 2 because of the cube there. And if you keep going and increasing your repeated roots at lambda, so you have right now L repeated roots at lambda. That would mean in the time domain, you have that factor there, 1 over L minus 1 factorial and t raised to L minus 1. So this can be used to deal with the inverse Laplace of repeated roots of Q of S. All right, I think that's good in order for partial fraction expansion. Let's continue our discussion of Laplace transform and how they apply to LTI systems in the next lecture.